We're Group 4. This is our presentation. This is our automatic control and instrumentation assignment 2 presentation. So our topic is ACC, also known as Automatic Cruise Control System. This is an advanced system for convenience and safety. Unlike regular cruise control, ACC adjusts the car's speed to keep it safe distance from the car ahead. It uses radar, LiDAR, and cameras to control brakes and throttle continuously, monitors road conditions and reacts in real time, reduces collisions and improves traffic flow. It helps reduce driver fatigue by handling repetitive driving tasks, as well as keeping the driver more alert and relaxed. And this is a step forward to fully autonomous driving vehicles. Now, in the research we've done, um, from the key benefits of ACC, safety improvements, as I said in the introduction, it reduces rear-ended collisions by up to 27% through continuously monitoring the traffic and adaptive braking, traffic flow and congestion. It ensures smoother traffic patterns and reducing congestion. It reduces the driver's workload and stress, allowing the driver to be more relaxed and more alert, and increases fuel efficiency as it optimizes the throttle and brake control compared to a human who, without active usage of the throttle and brake, make our fuel efficiency or reduce our fuel efficiency. Now, in the integration of ADAS and autonomous vehicles, ACC is a cornerstone for advanced driver assistance system, the ADAS, working along and keeping adaptive lane keeping and emergency braking. It represents a critical step forward to fully autonomous vehicles by incorporating automation and decision-making capabilities. From the technology behind ACC, as I stated in the introduction, it relies on sensors such as radar, LiDAR, and camera systems to monitor road conditions and adapt to real-time conditions. Sensor accuracy is essential for reliable performance, but can be affected by adverse weather conditions such as fog, rain, and so on. Now, challenges and ongoing research. Weather sensitivity, as I say in the previous section, weather sensitivity. ACC sensors perform poorly under extreme weather conditions. Researchers are developing sensor fusion techniques to address this algorithm limitations. So the pre-programmed algorithm struggle is uh, you can essentially not prepare for every scenario that could happen on the road. Unexpected scenarios such as um, complex urban infrastructure and just maybe reckless driving or unperceived uh, acts by people on the road may not be integrated into the algorithm, and therefore the system may not react accordingly because it's a foreign uh, action. While as far as future innovations, advances in AI, machine learning, and V2X communication aim to make ACC smarter and more adaptive. Now, from the market growth and adoption, as well as the future implications. So, the global ACC market is projected to reach 15 billion by 2030, driven by increasing adoption in mid-range and luxury vehicles, as well as automakers and tech companies continue to integrate ACC into smarter and connected transportation systems. Future applications include ACC plays a crucial role in the shaping of future transportation, contributing to safer and more efficient roadways, and also as a foundational technology of autonomous driving. ACC is expected to evolve further, addressing current limitations and unlocking new possibilities in mobility. Now, as far as the requirements for the cruise control, this is broken down to several sections. So, hardware, as we've said in the previous slide, so from the hardware is radar, lidar, and the cameras for the accurate distance control, speed, and obstacle detection. ECU for real-time data processing. On the software side, real-time algorithms for speed and distance adjustments, collision avoidance, and lane keeping integration. From functionality, adaptive speed and distance control, as well as fail-safe mechanisms for system reliability. Uh, on the environment section, all-weather capability, compatibility, and diverse road types. User features, intuitive driver interface and customizable settings, and for compliance, adherence to safety regulations and rigorous performance testing. Now I'll pass it on to my group member.
Hi, my name is Kui Jun Hong. I will be presenting slides 5 and 6. All right, so let's begin. Here, components needed. This slide outlines the essential components required for an adaptive cruise control system. Key hardware includes millimeter wave radars for detecting distances, cameras for visual input, and the ACC Electronic Control Unit, or ECU for short, which processes data and makes real-time decisions. Additionally, components like the brake control module, brake actuators, and wheel speed sensors work together to ensure a smooth and adaptive vehicle control. Each of these elements play a critical role in the functionality and safety of an ACC system. So next up, understanding a block diagram. So moving on, let's look at the block diagram. A block diagram provides a high-level overview of the ACC system. It organizes complex functions into key modules, showing their relationship and interactions. This is particularly helpful for understanding how input from sensors like radars and cameras flow through the ECU, which processes the data and sends commands to the vehicle actuators. Using a block diagram here makes it easier to visualize the integration of system components and their roles in achieving adaptive control. Now that we understand what block diagram is, I will now hand it to my fellow teammate, Liu Li Wei, to talk about the block diagram. Thank you.
This flowchart represents the decision-making process for adaptive cruise control system in a vehicle. This process begins with the initialization of sensor and control module, followed by the driver sets the desired car speed. The system continues the monitor distance to the vehicle ahead. If the road ahead is clear, the system maintains the preset speed. If not clear, it checks whether a safe following distance is maintained. It haven't safe distance ahead. Decelerate to match the speed ahead. If the vehicle distance too close, brake the car to stop, and if the vehicle distance not too close, maintain the speed. If it haven't safety following distance. If the vehicle has changed line, accelerate to the preset speed. The process repeat until system shutdown or vehicle stop. The flowchart highlight how the ACC system dynamically adjusts speed, maintains safe distance, and enhance both safety and driving efficiently. This diagram explains the adaptive cruise control system and its components for maintaining vehicle speed and safety. The process begins with a speed input provided by driver via a speed setting switch, which is sets the desired speed, and the system calculates the speed and distance error by comparing current car speed with the desired speed. The adaptive cruise controller processes the aero and adjusts through throttle through the electrical control unit, which manages the engine power, and send it to transmission to control the vehicle turbo. The turbo is applied to the wheel which determines the vehicle speed simultaneously. The system monitors vehicle speed using rotor encode. You can look this feedback and check the distance to the vehicle ahead via radar. If the radar detects a vehicle ahead, it sends a signal to ACC systems, this adaptive cruise control system, to adjust the speed, decelerate and accelerate the speed. If deceleration, the body control module BCN is used for. This one is used for reduce the car speed. Additionally, this disturbance, we added the disturbance because when some days it's raining outside and the ground is slippery. Talking about why we add disturbance in this location is because slippery ground reduce the friction so that affecting the speed of the vehicle in some rain days. Thank you.
As discussed, the current block diagram for the ACC is already working properly, but it doesn't take account of potential risks that may occur. As distance sensor has to be exposed at the front of the vehicle, we face an issue that it catches dirt and debris that sprinkles up from the road, which sooner or later covers the sensor up, resulting in malfunction. The measured distance will then always be zero. This is really dangerous if not handled properly. The ACC unit will brake abruptly as it thinks that a different vehicle is just ahead. Therefore, we incorporated a second radar measurement and a jet spray similar to windscreen washer jets that gets activated when the distance measurement returned by the first radar sensor is zero. This jet cleanses off any dirt and ensures accurate distance measurements and proper working of the adaptive cruise control. Next, it is quite common to encounter road irregularities, such as speed bumps, potholes, or significant surface damage, which can be dangerous if approached at high speeds. These obstacles, if not handled appropriately, can lead to discomfort for passengers and pose a significant risk to the vehicle. So far, the system is not able to adapt to that. To solve this issue of detecting obstacles that would cause damage to the vehicle, a camera-based detection system has been integrated into the existing setup. The camera scans the road ahead and sends data to the image processing block, which can recognize the distance to obstacles like speed bumps. If a speed bump is detected, an encoding signal is outputted. The signal is then sent to the adaptive cruise controller to reduce vehicle speed or even activate the braking control module to slow down the vehicle more quickly. This improvement ensures that the vehicle slows down safely when approaching speed bumps, preventing potential damage and providing a smoother driving experience.
The final improvement addresses adverse weather conditions, since they can have a big impact on the road surface. The car handling changes and get worse. Driving at a high speed under those conditions is really dangerous. Integrating environmental sensors into the system provides significant benefit by enabling real-time detection of adverse weather conditions, such as heavy rain, fog, snow, or icy roads. These sensors can monitor multiple factors, allowing the vehicle to adjust its speed accordingly for safer driving. For instance, reducing speed during slippery conditions minimizes the risk of skidding, while adjusting for low visibility ensures adequate reaction time. By proactively responding to weather-related hazards, the system enhances overall safety by reducing the likelihood of accidents during challenging environmental conditions. In summary, the result of the assignment demonstrates the block diagram and flowchart of the adaptive cruise control system, highlighting its key components. Issues such as radar inaccuracies and route disturbance were addressed by adding additional components, ensuring a more stable and efficient ACC system. ACC is a significant trend in the automotive industry as it will play a crucial role in future autonomous driving systems, serving as the backbone for autopilot functionality, especially during highway driving. That would be the end of our presentation. Thank you for listening.